My name is Keshav Pransukaka, and this is my lab report for Lab 3. The purpose of this lab was to calculate the net force and its parallel and perpendicular component on a star orbiting a black hole at all points in its trajectory, and to use that information to estimate the mass of the black hole. The net force at each point or after each time step was calculated using Newton's second law, while the mass of the black hole was estimated at each time step using Newton's law of universal gravitation. This calculation was performed using GlowScript Python software. From the unique trajectory of the star and average mass of 1.21 times 10 to the power 34 was calculated as the mass of the black hole. This is amazing because we are able to apply our simple knowledge of these two laws together information on one of the most powerful, strange, and fascinating phenomena that plays a key role in the shaping of our universe. One key concept used to analyze data is the momentum principle, which links the net interaction between a system and its surroundings and the observed motion of the system. The key concept here is that we can split the net force into some of its parallel and perpendicular component. From this, we're able to apply the momentum principle to directly relate that to observations we make of an object's momentum. Another key concept used in Newton's law of universal gravitation, which states that every object in the universe, including black holes, attract every other object in the universe with a force that is proportional to the product of both objects' mass and inversely proportional to the square of the displacement between both objects. G is a universal gravitational constant. In this lab, the net force on the orbiting star was assumed to only consist of the gravitational force exerted by the black hole. The initial conditions were inputted at the start of the code, where the mass of the orbiting star was set to 2 times 10 to the power 30 kg and delta t was set to 1 day, which is equal to 86400 seconds. So the main steps taken in the code were calculating the initial and the final momentum of the star. From there, Newton's second law was applied to find the net force on the star. The parallel component of the net force was also calculated using that law, being careful that the difference in magnitudes was taken rather than that magnitude of the difference. After that, the parallel component of the net force on the star was determined by taking the difference in net force and the parallel component of the net force. At this point, the net force and its components had been determined. Finally, since the net force on the star only consisted of the gravitational force on the star by the black hole at the origin, the net force was equated to the gravitational force formula and then used to find an estimate for the mass of the black hole after each step. For each time step in the while loop, the calculations mentioned in the previous slides were carried out. The initial, final, and change in momentum was calculated and used to find all the components of the net force on the orbiting star, as shown in lines 163 to 189. After that, in line 193 and 194, the mass of black hole was estimated using Newton's law of universal gravitation. Note that due to the simple approach of calculating the mass of the black hole, the mass calculated varied very slightly at each time step. The calculated mass of the black hole after each time step was placed into an Excel spreadsheet, where the average mass was found to be 1.21 to the power of 34 kg plus and minus 4% error. The 4% error was calculated by dividing the range of all the calculated masses by 2. Mathematically speaking, the net force and its parallel and perpendicular component are exactly the same as the rate of change of momentum and its parallel and perpendicular components. This equivalence is stated in Newton's second law of motion or the momentum principle and was used to calculate the force on the star. However, philosophically, these two dimensions are different. The momentum of an object, such as the orbiting star in this lab, can be observed and measured using information about the mass and velocity of that object. The forces on the object, however, can only be inferred from the rate of change of momentum. It cannot be observed directly. Well, now let's look at what happens when a different black hole was placed in the same location. The motion of the observed star is assumed to be the same, and the gravitational force due to the new black hole is assumed to be the only force on the star. Since the motion of the star is the same, the rate of change of momentum of the star is the same. Using the momentum's principle, this means that the net force on the star and its parallel and perpendicular components also remain the same. Finally, this means that the gravitational force is the same, which implies that the mass of the black hole is exactly the same as the first one. Hence, there would be no way to tell the original and the new black holes apart.